We now turn to the concept of the dark matter, which is where the most of the matter in the universe is. The original discovery of the dark matter was due to Fritz Zwicky in 1930s, who did a very simple experiment. He looked at galaxies in coma cluster, some velocities were measured. From that, he could derive the kinetic energy in coma cluster from virial equilibrium that told him how much total mass there has to be in order to bind galaxies together. And that turned out to be several hundred times more than the actual amount of mass he could see in stars. Nobody quite believed it at the time. Nevertheless, he was completely right, and the more modern versions of the same measurement have borne him correct. The reason why we believe that dark matter must be there is not just this one thing. There are many different methods that lead to more or less the same result. So here is how this works. In a system in a gravitational equilibrium, or virial equilibrium, the kinetic energy should be 1/2 of the potential energy to it in a sign. And for galaxies as test particles probing cluster potential, we can look at velocity dispersion as means of their kinetic energy per unit mass. That has to be balanced by potential energy due to their gravitational attraction. And that's how we can estimate mass of clusters of galaxies. We measure the velocity dispersion of galaxies through their redshifts, assuming that they're isotropic, so just the radial motion is representative of the two other components. Correct for that, measure the mean projected separation of galaxies, plug it in this formula, and derive a cluster mass. Typical cluster velocity dispersions are several hundred kilometers per second, or even up to a couple thousand kilometers per second for galaxies moving within the cluster potential well. Typical mean separation cluster radii are of the order, between galaxies are of the order of a few megaparsecs. Plugging these two numbers into the equation above gives us cluster masses of the order of 10 to the 14 or 10 to the 15 solar masses. At the same time, we can simply add up luminosity in galaxies and find out that the net mass to light ratio, that is mass of stars plus the mass of dark matter derived by luminosity from stars, is of the order of several hundred, exactly what Zwicky originally predicted. So clusters must be dominated by huge amounts of dark matter. A different way to measure that could be from the X-ray gas they contain. In addition to galaxies and dark matter, clusters also contain copious amounts of intergalactic gas. This is gas that was partly ejected from galaxies due to the supernova-driven stellar winds, and partly simply leftover gas from the original formation of structure that fell into the potential well. In any case, any test particle, whether it's a proton or electron or entire galaxy, has to move with same average velocities to balance the gravitational potential. So instead of hundreds of galaxies, we have untold numbers of protons and electrons serving as test particles. Their kinetic energy then translates into a temperature, which we can measure from X-ray observations, and thus we can find out what the velocity dispersion of particles is in a cluster. Turns out to be the same as in the case of galaxies. If we assume that clusters are on average in hydrostatic equilibrium, then that gives us a means of evaluating their masses directly from the X-ray temperature and their density profiles. And the result is the same. The typical masses of clusters are in the range of 10 to the 14 to 10 to the 15 solar masses, only about 5% of which is luminous mass that we see in stars and X-ray gas. Only about 1/6 is the stuff in baryons, and everything else must be the dark matter. A slightly different approach to this is to measure the baryonic fraction in clusters of galaxies. So the fraction of the total mass in baryons is the sum of fraction in stars, in gas, and in dark baryons, which, as we already learned, are actually in form of X-ray gas. So if we assume that that's a fair mix, that mix in clusters, which are the largest bound structures we see, is the same as the universe at large, then it gives us an opportunity of actually estimating omega baryons or omega dark matter. We do have to assume omega baryons from nucleosynthesis, and that is a fairly reliable measurement from microwave background and from cosmic nucleosynthesis. The physics of that is well understood, That's a fairly well-established number. So roughly speaking, 15 or 20% of mass in clusters is in form of X-ray gas, and that gives us limits. At the same time, we can say what is the lower limit to the fraction of baryons, and also what is the upper limit on omega matter. A more detailed analysis, which also includes mass in galaxies, then yields to the typical baryonic fraction clusters of the order of 15%, and the omega matter total for clusters of galaxies, which we can then assume is not different from universe as a whole, of the order of 0.25. This is in an excellent agreement with completely different measurements obtained by other means that we covered in cosmological tests. The second major piece of evidence for the existence of dark matter are the rotation curves of disk galaxies, spiral galaxies. And they all tend to look more or less the same. There is a rapid rise in the middle, and then the curve becomes more or less flat all the way we can measure it. It's only in the more modern days that people manage to measure them so far that actually see them decline. But for the most of the extent of visible galaxies, by visible I mean both stars and gas, the rotation curves remain fairly flat. This has very important consequences. We can decompose rotation curves to the contributions from different components. The gas is moving in circular orbits, roughly speaking, and centrifugal force is equal to centripetal force, so we can derive the total amount of mass inside a given radius. We can simply add up the mass that we see inside that radius in stars or gas. And from that, we can see that out to radii of several kiloparsecs, like solar radius in Milky Way, visible stuff does dominate the total gravitational potential. But then further out you go, its contribution drops down, and something else must be contributing the mass that requires high circular speeds. If you think in terms of, say, solar system, the velocities of outer planets are much slower than the velocities of the inner planets, for the reason that gravitational potential in outer regions is much weaker. And if there were no dark matter, something similar would apply to galaxies. So the argument is really very simple. This is the most elementary Newtonian dynamics. If you have test particles orbiting in circles, which is more or less correct, we can immediately say what is the mass inside of that circle. Now, if we only take luminous mass, we can come up with a model that predicts what circular velocity should be as a function of radius. And in the inner parts of disks, that's not so bad. But then, in the outer parts, the model predicts that velocity should be declining, and it doesn't. That means that it has to be, there is a missing component in the model. So measuring the circular velocity as a function of radius gives us a direct estimate of the mass inside that radius, and therefore, what is the density as a function of radius. If we assume that it is a power law, we can, and this is a reasonable assumption, it turns out that flat rotation curve, as shown in a simple evaluation here, so it's very easy to derive that a flat rotation curve implies the density law that is behaving as radius to the minus second power. That is called singular isothermal sphere. It's singular because density goes to infinity in the middle. This is obviously not the case in reality, but small rounding off in the middle make no difference here. It's isothermal because the velocity is the same throughout. If you integrate density distribution like this in a sphere, you get mass that increases linearly with radius. Recall, if the density was constant, the mass would increase as a cube of the radius, but because the density declines as a square of the radius, then what's left is just 1 power. Which means that as far as we can trace the rotation curves of spirals, and they stay flat, the mass keeps increasing. And until recently, we didn't really know where it stops. You can do a very similar thing for elliptical galaxies, which is essentially the same thing we've done for clusters. There, the orbits of stars are fairly random, and we cannot make circular orbit assumption. We can follow velocity dispersion of stars, and that will do more or less the same thing. But we can also use gas, because elliptical galaxies do contain copious amounts of X-ray gas, and the treatment there is exactly the same as we did for clusters. And the answer is that in the inner visible parts of the elliptical galaxies, visible material dominates the gravitational potential. But as you go to ever larger radii, the contribution of the dark matter does increase. Instead of the X-ray gas, you can use other test particles. In case of elliptical galaxies, those could be globular clusters or dwarf galaxies around them. And even though their numbers are much smaller, they produce exactly the same result. There is one kind of galaxies that is actually completely dominated by dark matter, and those are so-called dwarf spheroidals. These are dwarf galaxies. The Milky Way has of the order of 20 of them orbiting around. They do not contain much in terms of stellar mass, maybe millions to 100 millions of solar luminosities, but they do seem to contain a lot of dark matter. And we evaluate that in exactly the same way as before. We use their stars as test particles, probing the gravitational potential. We measure their velocity dispersion, function of radius, and we derive the amount of mass needed in order to bind these stars to a galaxy. The mass-to-light ratios reached levels of 100. Recall that for a pure stellar population, the mass-to-light ratio would be of the order of few. And so therefore, there could be a large amount of dark matter in these galaxies. There is a reasonable physical model how that can happen, that the supernova-driven stellar winds can expel a lot of gas from a galaxy, but they do not expel the dark matter because it does not react to the pressure. It's just bound gravitationally. And there is one more way in which we can do this, and this is by using now velocity of galaxies on large-scale structure. Overall, measuring the peculiar velocities of clusters and groups, inferring what the density field is from them to have such velocities, and then averaging to find out what is the overall matter density corresponding to such a velocity field. The answer to that, again, brings that omega matter is less than 0.3, but it's probably more than 0.2.